Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I'm dealing with chemistry topic thermodynamics. In this topic, this is lecture number 32 and this lecture is related to entropy. Entropy is a very important word which is used in thermodynamics and it is related to second law of thermodynamics. So first of all, let us understand the definition of entropy. So entropy is a measure of randomness or disorder of a system. Well, this is the definition of entropy, but in fact, there is no synonym of entropy, and that is why these two words, randomness and disorder, are used to explain what is entropy, but these are not the proper words to be used. But there is no other choice because entropy has no perfect synonym. So entropy as such, if you see the definition or numerical conditions of entropy, it is related to entropy change is equal to dq reversible upon T, and the unit could be calorie per degree or joule per degree. Okay, so this is related to heat changes definitely and temperature. But if we want to understand entropy, then we have to consider a common day-to-day life experience of entropy. So how can I explain you entropy? See this. Suppose you want to purchase or buy a pant for you. Okay, and it can be a jeans. Definitely your choice is a jeans, and money is not a constraint, so you can buy it with, you have enough money to buy jeans for that. So obviously you will go for a brand. So you will go to the most famous shop of your city to purchase or to buy a jeans, and this may be for the first time for you to buy a jeans. So you will go to any one shop, and the moment you enter into the shop, the salesman will come to you and ask you what you want, and you will say that you want to buy jeans. So definitely he will take you to the certain place where you can see different types of jeans. So the salesman can show you various types of brands, various types of colors, and various types of styles in jeans, and all are excellent. That means you have to select the best for you, and you realize that all are best for you. So the problem of selection appear over here. Okay, so problem of selection, that you cannot select a proper thing for you, and that create a stress, strain, energy, etc., and that is known as entropy. So when a question of selection appear, entropy appear. Okay, so this is the way we can understand entropy. Now let us consider this with reference to uh, thermodynamics. So we will take entropy change for an ideal gas. So entropy is a state function. Remember that. It is a state function. That means it does not related to root. It is related to position. And its value depends on its value depends on two the three variables of thermodynamics, that is temperature, pressure, and volume. So first of all, let us see when temperature and volume are as variables. So let us consider n moles of an ideal gas occupying volume V at pressure P and temperature T. If the system absorbs and dq reversible heat reversibly, then so increasing entropy is given by ds is equal to dq reversible upon T. Now, first law of thermodynamics says that dq reversible is equal to dE plus P dV. Okay, so this is equation 1. Now substituting the value of dq reversible from equation 1 to this equation, this formula, then ds is equal to dE plus P dV upon T. This is equation 2. For n moles of ideal gas, you know we have formula P is equal to nRT upon V. So, and dE is equal to nCV dt. Okay, and where Cv is heat capacity at constant value. So substituting values of P and dE in equation 2, we will get ds is equal to nCv dt plus nRT upon V into dV upon T, or ds is equal to nCv dt upon T plus T and T will be cancelled, so nR into dV by V. This is equation 3. Okay, so if the volume, if the entropy, volume and temperature of the system in initial state are S1, V1 and T1 respectively, and in the final state they are S2, V2 and T2 respectively. Then integration or integrating equation 3 between these three limits, we get integration of ds from limit s1 to s2 is equal to integration of t1 to t2 n cv dt by t plus from v1 to v2 nr dv by v. Assuming cv to be independent of temperature over the temperature's range, then and delta S is equal to S2 minus S1. So here we write delta S is equal to N Cv ln T2 upon T1 plus Nr ln V2 upon V1. This is equation 4. And for 1 mole of an ideal gas, delta S is equal to Cv ln T2 upon T1 plus R ln V2 upon V1. This is equation 5. Or we can convert this into log so that we have delta S is equal to 2.303 Cv log T2 upon T1 plus 2.303 R log V2 upon V1. So this is the main equation with the help of which we can find out entropy change in this condition. Okay, so I think that's it in this lecture. Thank you so much.